Hey, it's Mr. K doing a video for AP Physics C and for Physics 1 if you want to catch on or tag along with us here. We're going to be talking about vectors, vector kinematics, vector addition, vector subtraction, trigonometry. Really, it's not as hard as you might think. You just gotta sit down and understand what it is to use sine, cosine, and tangent. Pythagorean Theorem, everybody's favorite equation, and let's hit it. So. A lot of times in physics, a lot of times in math, most times actually, you're going to be working with one dimension, which means, think about how you would add. How would you add 5 and 3? Well, you would put your hands together and then you would count how many fingers you have up. Well, on a number line, as you've learned from, let's say, first grade onwards, you've seen how a number line, if you want to have 5 and 3, you would count over 1, 2, 3, 4, 5, and then count over another 1, 2, 3, and that is addition on a number line. If you wanted to take 8 and you wanted to subtract 3 from it, you'd go 1, 2, 3 back the other way. And so addition, subtraction, multiplication, division, really you're working with one dimension. And dimensionality, a lot of times chemistry just really screws with your head because you think dimensional analysis is like a super hard thing. But all it says is that we need to work with the same units, the same dimension in order for us to do anything. Okay, it's like working with currency. I can't talk about working with dollars and cents, the American currency, and then go over to talking about euros or yens. You got to convert in order for it to work out, or else I'm ripping somebody off. So let's talk about this dimensional analysis. Let's talk about working with dimensions, and we're going to work with, at maximum in this class, we're going to work with 2 dimensions, spatial dimensions, and then time. All right, so as for anything to happen, it takes time, but if we want to have, where did the ball go? If we want to have this ball dropping straight down, fantastic, we can. That's in one dimension, straight downwards. I can toss it up and it falls back down. That's in one dimension, up and down. But then if I wanted to do this, that's going to be in 2 dimensions, left, right, up, down. And then in order for anything to happen again, it takes time. So let's talk vectors. Vectors are what we're going to be using to describe things that have magnitude and direction. And in order to talk vectors, well, we might need to know a little bit of trigonometry as well. So, if I say that Peebs, where'd you go? She's there. She's back there. Right. If I say that Peebs is going to run in a straight line, and we're jogging, we're probably going to take a jog in like an hour. It's the morning time. It's summer. I'm trying to do these in the morning because it's hot. Well, if Peebs is running and she's going to run she runs pretty fast, let's say like 8 meters per second, she's sprinting, and she goes for 5 seconds, how would you draw that, right? So in order for you to really describe it, we would say, all right, well, here is Peebs. I'm not going to take time to draw my dog. In class we might, but you would say that she is moving at a rate of, let's say 8 meters per second. We're going to put those units on there. And I'm going to denote forwards for her to be to the right on the paper. And here we have her moving for a total time of 5 seconds. And so her velocity is 8 meters per second. Her time to move is 5 seconds. And what we would get from that is another vector, which would be 40 meters long, because that's how far she would have gone. And I would draw another vector that's to the right, that's 40 meters in however long that would be represented by here. Now, if I said, all right, well, she's going to slow down, and later on, she can't run at 8 meters per second the entire for forever. She's going to run, and after 5 seconds, she's going to slow down to 2 meters a second. She's going to slow down to a kind of a trot, right? So, well, 2 meters per second, relatively speaking, would be something like this. It's 2 meters per second. Okay, and so how did we how do we get there? Well, we had to change the length of her velocity vector from 8 down to 2 meters per second. Well, how do you do that? That means that you had to take away 6 meters per second from her velocity. Well, how do you change velocity? Well, this goes back to your basic definitions again. Acceleration is a change in velocity over a change in time, and you better bet that in order for us to change this velocity vector from 8 to 2 meters per second, she had to accelerate over a certain period of time. Now, the quicker she does it, the higher the acceleration is going to be. The slower she does it, well, the lower the acceleration is going to be. But what we know is that whatever her acceleration was, whatever time that she took to do it, that change, it's going to change the velocity by -6 meters per second. Okay, so here we have the math function that says, hey, we accelerate for a time based on the acceleration, we're going to get a change of velocity of -6 meters per second. That's going to change her velocity vector from longer to shorter, and that should make total sense, right? And so what we need to understand is that there would be a way to do that. So here we have the velocity vector that was 8, now it's 2. What that means is we would have had to add another vector to it that was 6 long in the other direction. Okay, so if this is 8 meters per second and this is 6 meters per second, then this resulting vector, the resultant vector, should be 2 meters per second, and that's going to be still to the right. And so we have a visual, a graphical way to show addition, or in this case, subtraction, right? So, well, it's actually still addition because we're adding these two vectors together. So there's this thing called the tail-to-tip method, the tip-to-tail method, where you put one vector on the tail of one on the tip of the other one, and whatever you get at the end would be that resultant. So here, let's try this. Let me actually switch colors here. I have 8, which is going to be represented by the red. I've got the 6, which is going to be represented by this blue one. And as you can see, what we have at the very end would still be this vector that would point to the right there, and that would be our 2 meters per second vector that we had originally. Now we're gonna expand on this. You know, we could have 8 plus -6, right? It goes the other way, -6 in the x direction. You bet we can do it in 2 dimensions. You bet we can do it in 3 dimensions. But before we do that, let's just do one more thing. What if we had the same problem, 8 meters per second, but instead of plus, it was minus. -6 meters per second. But that's 6 meters per second to the left. Okay? And so, you know, just think about how you do math right now. The problem that we did initially was basically 8 plus -6. That's what it was. It was 8 plus -6. 8 plus -6 is 2 meters per second to keep the units on there. The problem we have now is saying 8 minus -6. Well, how does that work with math? Negative. Cancels out and makes a positive, right? So to subtract a vector is simply to add its flipped around state. You just flip it around. Okay? All the negatives become positives, all the positives become negatives. So this 8 minus 6 to the left is actually going to be like saying 8 plus 6. And so that's going to be 14. So this should be a 14 long vector. 1, 2, 3, 4, 5, 6, 7. For squares here, if I'm doing that right. 14 meter per second vector, and that's going to be to the right. Okay? Let's make this a little bit more difficult. Let's go 2 dimensions. You know, you can set, and this is going to be important later, you can set your vectors, you can set x and y to really whatever you want. A lot of times what math does for you is it makes you think that x and y have to be horizontal and vertical. Okay. What I mean by that is, who's to say that this couldn't be y and this couldn't be x, right? I know I drew a diagonal pink line, a pink arrow, and you would be, you know, initially just wanting to go like, hey, that's y and that's x right there. And so this diagonal pink arrow would be going in x and y. But if that's the only direction that you care about, if that's the only direction that really is being worked with in this problem, why not just make that one of your principal axes, x or y? Okay. You know, if you have somebody driving down the street, and you want to clock them, say, oh, you're going 50 miles per hour. That's great. But did you ever consider that they might have been going like 50 miles per hour northwest? Did you even care about that? No. That just complicates the problem. You just assume that they're going straight. So, in the cases where we can't do that, that's where vectors are going to be useful for us. Where we have this pink vector and it has something called components. And so the components to it, we're going to use red and green. This pink vector has two components. It has a component in the vertical direction. It has a component in the horizontal direction. I'm not sure if red and pink are going to be differentiable. I should have used blue. I don't know if that's going to be differentiable either. I'm just going to stick with it. Anyway, so we have this 1, 2, 3, 4, 5, however, whatever units we have here in the y direction, and then we have 1, 2, 3, 4 in the x direction. And so, if you go into engineering, a lot of times you're going to be talking about I, J, K vectors, unit vectors. I, J, K just represents x, y, and z. And we often talk about these vectors in their component forms, because if I just say, 8, what am I actually talking about? It could be 8 straight up. It could be 8 to the right. It could be 8 to the left, backwards. But we don't know. But if I said something like 8 in the x direction, 0 in the y direction, we know that this thing only goes to the right. And so here, that's what we're going to do. So we need to be able to break this vector down into its components, and we need to be able to put those components back together. So here we have 4 in the x direction, we have 5 in the y direction, and if we wanted to put those back together, we would be able to find whatever this diagonal was. Now, how do you put the two sides of a triangle together? Because really, don't forget that you can just kind of move this over, and the 5 also measures this side over here. How do you find the diagonal? And that's going to be using Pythagorean Theorem. So a squared plus b squared is equal to c squared. And we've got 5 squared, so 25, plus 4 squared, 16. And we're going to square root that. It's not going to be very nice. It's going to be 6.403. So this is 6.403 as far as the length of that vector goes. And then that's great, but again, it doesn't really help you out with the direction. So if you want to be very specific in this two-dimensional plane, we got to give an angle. And so we're probably going to give this angle down here. And this angle, we're going to call it theta. Theta, T-H-E-T-A. And theta is going to be found by doing a little bit more trig. Now, you might be afraid of trigonometry. It might not have treated you well. You might have been all like, oh my gosh, why is this so difficult? It's probably because you just never cared to actually sit down and study it. Just for a little bit, and then it becomes nicer. So, let's use some trig here. We want to find an angle. We've got all the sides to my triangle. I can use sine, cosine, or tangent. Now, these won't find us the angle. These are equal to the ratio of two sides of my triangle. The thing that's going to find us the angle is going to be that arc sine or inverse sine, cosine, or tangent. But let's get this out of the way first. Sine. That's a little acronym here. SOHCAHTOA. SOHCAHTOA. And this tells you what the ratios are. All these three things are just ratios of two sides of a triangle. That's all it is. The sine of the angle is equal to two sides, the ratio of those two sides. So sine of theta, sine of that, is equal to the ratio of the side that is opposite over the side that is the hypotenuse, which is the longest side. Cosine is the ratio of the side that is adjacent over the side that is the hypotenuse, the longest side. Tangent is just the ratio of the opposite over the adjacent. Okay, and so we have these three things that we can use to figure out the sides of a triangle. Right now we want to figure out the angle. So we have all three sides of the triangle, which means that any of these are available for us to use. I'm going to use 5 and 4, the opposite and the adjacent side, because I know that I didn't have to calculate those. Sometimes we do a calculation and then we round, and it's going to kind of screw up that hypotenuse there. So I don't want to rely on an additional step to find a number. So 5 and 4, opposite and adjacent, that's going to yell tangent. And so I'm going to use tangent, in fact the inverse tangent, to find out what the angle is. And if you type in inverse tangent, like second tangent, you need to put in the ratio of the two sides that tangent relies upon, 5 and 4 in this case. And if I do inverse tangent, we're going to make sure that I'm in degree mode. Inverse tangent, second tangent, of 5 over 4 gives me about 51 degrees, 51.34 degrees. So this is 51.34 degrees. And that is the angle here, 51.34 degrees. But we're going to be a little bit more specific, and we're going to say this is 51.34 degrees north of east. And the reason why I say that is because if we just say 51.34 degrees, there are many 51.34 degrees that we can talk about. 51.34 degrees from the north to the east, which would be this angle up here. Could be west of north, which is like this angle over here. So you want to be really specific. So we're going to have to practice this a lot. It's going to be on you to practice it. You know, I'm going to go over this a couple times, but you really need to practice this in class on your own as well. Let's go ahead and actually just finish up this video, and then we'll do an example problem. All right.